Good morning. My name is Dennis Burrell with Ventive, and this is your last presentation before lunch, so I'm standing in between you and lunch, so I won't take all of your time. But so we're going to talk today about Antenna University and how do we do it at Ventive. I'm Dennis Burrell, has my email address and my Twitter handle. The way that we came up with this is I participated in a few of the Wi-Fi of Everything broadcast on our YouTube, and we were talking about antennas and antenna designs and small form factors and how we go about designing those. So during that time, a couple of questions came up. Well, how do you guys go about doing that? What are the parameters that you go about doing that when you're coming up with your designs? What do you take into account? What types of structures do you use? So it drew a lot of interest, so we decided to just do a presentation on it. So what is our antenna design and test process? And this is pretty much an overview. So the main thing is we create a spec definition. So what do we want the antenna to do? What types of gain do we want? The beam widths. Then we go through a numerical analysis exercise, and that's to actually design the antenna. We do a design package for bidding. Then we go to a manufacturer selection. Once we select the manufacturer, we come up with design files. Then we actually do a sample, build, and test. We go through pre-production approval, golden sample review, and then ultimately production. So we're going to talk about design. So I guess this slide will help you get ready for lunch. So every taco is unique and different. As you can see, I'm a taco guy, I love tacos. And then we also have the 5 taco love languages. So everyone uses these every now and again. So what we're trying to say here is that every design process for an antenna is different. You have your standard types of structures that you use to design the antennas, but that's pretty much where it ends. So then you have to go through your feed structure, your impedance, your visual, all of those different parameters when you do the design. So every design is different, but you start with the standard building blocks. Is it going to be a patch antenna? Is it going to be a microstrip antenna? Is it going to be a dipole? And then from there, that's where you go and characterize it specifically for your application. So let's go over some of the things we look at in the design process. So once you have your spec that you want, then you want to select the antenna type. So what is going to be your operating frequency? Is it going to be a single band or a dual band design? What polarization do you want? Is it going to be vertical, horizontal, dual polarized antennas, slant 45 or circular? Pattern, are you looking for omnidirectional or directional antenna? Is it going to be indoors or outdoors? And then beam width, are we talking a narrow beam width or a wide beam width antenna, depending on your application? Then the antenna size and the feed network, which is dictated by the gain of the antenna. How much is the gain going to be? What's the beam width, both horizontal and vertical? Your side lobe level, and then your front to back ratio. And then we want to go through an antenna synthesis. So this is what we're going to do. We're going to synthesize the feed network, right? What's the impedance? What's the length of the feed network going to be? And this is derived by the side lobe level and also the number of radiators used to achieve the gain. So for instance, for a higher gain antenna, say 10, 15 dBi, you're going to need more so of a array structure to get the gain that you need. So what type of structure are you going to need or synthesize to get the gain that you need for your antenna? So let's go through some of the things that we look at on the design process. So also, then we do CST simulation. So that's the design package that we use for numerical analysis. And so you have to select your simulation parameters. What are you going to focus on when you first start designing the antenna? Is it going to be the gain? Is gain more important to you than in beam width? If it's a high density design or a stadium design, and you're looking for a very narrow beam width antenna, that's going to be more important. You'll want the beam width, and then whatever the gain is to get you the beam width, you'll take that, but it's predominantly the beam width that you're looking for. So the way that we go through the design is we come up with a single radiator geometry. So we take the radiator, a single radiator, and we optimize that radiator for visual over the frequency band, and like I said, to achieve what the beam widths you want, and then port-to-port isolation if it's a dual band design. Then we simulate and optimize that feed network for a single radiator. And once that's complete, what we do is we just replicate that depending on the ports that you need or how many ports you need on your antenna. So if it's a 4-port design, we replicate that 3 more times to come up with a 4-port design. And then once we have that, then we optimize that based on spacing so that you keep the parameters or the specifications that you achieved for the original 1-port design that now you're replicating it. And since you're going to have space in between them, you may have some mutual coupling. So you have to work with the spacing to make sure that you achieve similar gains and beam widths on each of the other ports that you replicated. And so then we run a tolerance and sensitivity analysis. What this is that you want to take into account if, for instance, if you're using metal to fabricate your antenna, what are the tolerances on the metal that you're using? What's the thicknesses? If it's a PCB design, what are the dielectric of the PCB? What are the variations on that dielectric? What's the variation on the thickness? Your feed lines, what's the variation when you go to fabricate that as well? Once that's done, we generate assembly drawing using SolidWorks. We get it built, and then we test it. So for the feed network and antenna size, let's look at gain. So in gain, when you focus the beam, you get more distance, right? So, but when you focus that beam, one thing it does is it reduces the possibility of RF interference from nearby systems, right? But then focusing it, you can focus it horizontally, vertically, or in both, but nothing is free. You lose coverage in other directions when you focus it. So if you want to look at an antenna, so antenna gain is specified in dB isotropic. So isotropic antenna pretty much radiates all over. It's a perfect radiator. So if you assume a light bulb in the room, when you come in and turn a light bulb on, it illuminates the room. That's what we look at as an isotropic radiator. For a medium gain antenna, assume that you have a flashlight. And you know how when you turn a flashlight on, if your batteries are getting ready to die and you hit it and you just barely get a beam out of it, that's what we would say is a medium gain antenna. Then a high gain antenna is look at a flashlight that you turn on and you have brand new batteries in it and it goes all across the room. So that's pretty much a narrow beam, which we would say is a high gain antenna. So beam width. So the beam width is the size of the lobe in degrees where 90% of the power is radiated. And typically beam width is designed as the point 3 dB down on either side of the peak of the antenna. And in this case, the beam width for this is 26. So that's typically how beam width is specified, but in some high gain environments, we've had customers come up and say they wanted, what is the beam width at 10 dB down, because they want to make sure that there are no side lobe levels that's going to interfere if they're doing a high density stadium design. And then you have side lobe level. So the side lobe level is the amplitude off peak of a lobe in comparison to your peak lobe. So in this instance, the side lobe level is around 8 to 9 dB. Then finally, the front to back ratio. So this is important in high density design, specifically stadiums. For instance, if you're doing a handrail design and you have antennas and you want to illuminate a section, the front to back ratio is the difference between your front, your main beam, and the back lobe, or the beam that's shooting out the back of the antenna. So if you have a low front to back ratio, that means that you're radiating, for instance, if you're looking at a stadium and you're radiating in the stands, or if you go to the opposite side, if you're getting radiation on that side, then that's the front to back ratio. And you want to, and one thing to remember is it's 180 degrees from the main beam. So you may have some back lobes, but the front to back is where the peak is. 180 degrees from that peak is how you specify your front to back ratio. So let's talk about simulation. So like I said, we use CST simulation, and that's pretty much a numerical analysis package where you put in all of the parameters and you specify the main parameter that you want to solve for, and it goes through the calculations based on what you set your specs for. So this is a simulation of a high gain antenna that we looked at. So what we did was, if you look at it, it's a four element array. So we took one of those, then we optimized that. And once we had that, then we replicated, because it's a 4-port antenna. One of the other things that you can do in your simulation is you can actually model your radome as well. Because once you put your radome on your antenna, it's going to shift the resonance frequency that you design for. So you can actually design for or simulate your radome as well, so that when you actually get your radomes and build the antenna, all of that's taken into account, so you can design for the proper frequencies. And this shows the return loss of this example. Then you can also do cuts of the antenna. So you can look at the elevation and the azimuth in your simulation as well. And then once you actually build and test, you can compare to see what the simulation looked like compared to your actual numbers that you tested at a third-party lab. Manufacturing selection. So how do we select our manufacturers? So we look at a lot of different things. Development price, production price, and order quantity. So typically, when you get your antennas, you order based on a set amount, and based on that, you get your price, and then the more you order, the more of a break you get. Typically for you guys as well, when you buy or purchase antennas as well, the more you get, the more of a discount you get. What's the development schedule? How long is it going to take to actually get product? What's the final antenna specification? So although we provide what we want it to be, once you go through and start manufacturing, they may be slightly off. So if we're comparing manufacturers, we're going to look at how far they off compared to what our specifications are. And then we also look at a social responsibility aspect of our manufacturers as well. Workers should be 18 or older. Work conditions should be safe. The work environment. Workers should not be forced to work more hours than local regulations. Just different things. And more importantly, workers should not be exposed to sexual, ethnic harassment or discrimination. So we take all of those things into account as well. Now, we do manufacturing both in the US and overseas. So how do we make sure that these things are taking place? So when overseas, so we work with logistics companies that go in and audit our manufacturers, audit the process, and also audit the antennas when they're coming off the line to make sure that they meet spec. If they don't, we'll fail the antennas and we'll go and put in a process to make changes. So now we're going to talk a little bit about testing and sampling. So this shows some visual testing that we can do in-house, and we'll set a pass-fail for it, and we'll test all of our antennas for visual. All of our antennas that we, when we're designing and we start going through and sampling, we'll send them out to a third-party test lab, and we'll get data on them. So this is a high gain antenna that we're working on, and it's a 5 gig only. So as you can see, we tested the antenna in 50 megahertz increments over the 5 gig band, and we overlay them on each other so we can see what happens with the frequency. As the frequency varies, what happens with the antenna? Does it shift off axis, or is it still at the peak at 0? The side lobe levels, if they go up and down, and then we take these and then we can modify the antenna or go through iterations to fine tune the antenna. So one thing to remember when you're going through chamber testing is that you can pretty much do, when you're going through and doing your measurements, you can do any subset of the frequency. So this is 50, but if you wanted to do 10 or 20 megahertz, you could do that as well. But the more cuts or the more testing that you do, the more time consuming that it becomes. We also had the capability to look at the 3D results of the testing as well. And with this, so this just shows that same antenna 3D, so you can see the colors, and the colors, the darker the colors, the red is the peak of the antenna, and then as you go down to the blue, that's the level or the gain of the antenna in those areas. And we also have a software where we can actually take cuts of this antenna, and we can look at it at 90 degrees, phi equals 90, phi equals, and we can do different cuts on the antenna to see how the antenna performs in different orientations as well. And then we can get a spreadsheet that pretty much shows the frequencies that the antenna was tested at, the peak gain of the antenna, the location of that peak gain. And as you can see, this one was at 0 degrees, so it was right on where we designed it to be. What the minimum value was, the location of that, and then also the beam width of the antenna, and then a max to min. And then in some instances, if we working with one of our customers, we can say, hey, can you take our antenna and go and actually test it? So we worked with one of the customers, and they took this antenna to one of the NFL stadiums, and what they were looking for is something that they could test or utilize on the field when there were concerts, but not a football game, and they needed coverage on the field. And so this antenna was tested 200 feet up, and eventually what'll happen is you see the transom going across, the antennas will be mounted on that, and then they'll be for coverage on the field. So that's an added feature when you can get someone to actually go and test it while you're still going through the design process and give you feedback on it. And so then golden sample approval. So we look at the specifications to make sure to see if the vendor that we're looking to choose meeting specifications. Then we actually do a visual inspection of the antennas. We'll look at the radome, see if there are any blemishes, any discoloration, look at the quality of the soldering, look at the cables to make sure everything is good. And then based on that, once we approve, we'll go into production. So the next thing I want to look at is a competitive analysis. So we're a third-party antenna manufacturer. So all of the ODMs, they have their own antennas. So if we want to position an antenna to you guys, we want to make sure specifically if it's an equivalent antenna that it actually is equivalent to what's out there. So we'll go through a competitive analysis real quick to show you some of the things that we look at. So that's the competitor. That's the OEM's, for instance, antenna or the competitor's antenna. We want to be the same, but we don't want to be a ditto. We want to be that or above. So we want to look at different things. How can we how can we balance it? So for instance, if we can do a price comparison, quality or size, if we can come up with something like that to make it beneficial for you as a user, to give you something to look at when choosing and selecting your antennas. So how do we stack up? So this is my little ode to game night. That's the old Tekken, if anyone remembers that. So how do we come up with our equivalent antennas, and how do we compare the antennas to the competition? So the antenna we wanted to look at was the 2566D4M Cisco's, and this is their spec. We just purchased an antenna and we took it apart, and as you can see, this is the inner workings of it. So they pretty much did a folded dipole design, full-wave dipole design, and it's a dual polarized antenna, 6 dBi peak gain. The beam width's 65 and 60 on the elevation, and 65-55 on the azimuth. And one other thing, look at the size, 10 by 10 by 1.6. So those were the goals that we were trying to meet. So our design approach was to use dipoles because dipoles naturally give you a 60-degree E-plane beam width. But in the horizontal, it's typically around 120 degrees. So what we did was we paired two dipoles together to narrow down that beam width to that of a single dipole to try to get a 60-60 design. So the spacing in the H-plane, we adjusted that to bring that down to the 60-degree beam width. And one of the things that we do to actually make our antennas small is that we interleave the 2.4 and 5 gigahertz elements. So what that means is that we design for the 2.4, and then in between the two radiators of the 2.4, we actually place our 5 gig radiators in between those. And then we go through adjustments and try to compensate for it to make sure that both are operating at the correct frequencies and giving us the gains that we want. And by doing this, we can actually make the antenna smaller. Further, for gain reduction, so when we say specify the gain of our antenna, we specify it at the actual connector, so the cable loss is taken into account. So for this antenna design, we was looking at RG58 cable. We want to have 3 feet pigtail, so 3 feet loss is 1 dB at 2.4 and 2 dB at 5 gig. So we designed the antenna at 7 and 8 respectively to take into account the loss that we're going to see through the cables. Then we use a diplexer to split apart the 2.4 and the 5 gig. And then we add poles to the diplexer so that we could achieve isolation. So the more poles we add, the more isolation. And I'll show you a picture later to show you what I'm specifically talking about. So we want to design this on the FR4 board as well. So everyone knows that, or if you don't, but FR4 has a lot of losses from batch to batch. So you have to take into account the losses as well, and the length of the microstrip transmission lines. We play with that until we have a gain around 6 dBi. And then the trick is, once you go into production, to find a FR4 that has a constant variation over time. So we actually found one that we have about 20 years of data on that has a very tight loss over frequency over a 20-year period of measuring it. So we took this to a third-party lab, and we tested both of the antennas. On the left is the Cisco, and on the right is our design. So as you can see, for the peaks and the average, we're right around 6 dBi. But more importantly, if you look at the 5 gig on the Cisco compared to ours, we're more closer to 6. In some places, we're outside of 6. And this falls into the half dB variation, correlation error on the chamber as well. But this is something that we actually went back and designed, went through iterations to bring this under 6, but I just wanted to show you this comparison. This is actually the first one that we built and we went and tested it. So over the 5 gig band, you can see 2 to 3 dB better performance and gain compared to the Cisco antenna. So then we also looked at the beam width. So we tested each port, the beam width for each port, and then we did an average both on elevation and on the azimuth. And these show the numbers here. So we were pretty constant on both the elevation and the azimuth on our design, around 57 and 54 respectively, both on elevation and azimuth for both 2.4 and 5. And then those are the Cisco numbers. So then we wanted to look at patterns as well. So these are the 2D patterns that are 2.45 and 5.5 of the antennas. And you can see, based on the beam width that we spoke about previously, you can see around the 3 dB beam width what's the variation between the Cisco and the design that we looked at. And then in some aspects, when you look at the Cisco design, it's wider and has a little more ripples in the 5 gig than we have in our design. So if we look at this equivalent spec first pass and you look at the antenna, if you look at this, this is what I was talking about as far as the 2 furthest radiators are the 2.4, and by interleaving, when I said we placed the 5 gig in between, so as you can see, the 5 gigs are placed in between the 2.4s, and then we optimize the antenna's performance based on that. And then the poles are the orthogonal lines off of the microstrip feed lines, and that's what we use to get the isolation between the different ports of the antenna. And this actually was tested with a 3D printed radome. So the radome, the parameters of the radome that we put in CST would further knock down the gain of the antenna as well because of the dielectric of the radome that we would be using. But we went and 3D printed this so that we could actually get it out and do testing. And then if you, the most important thing as far as what we set the specs as far as what we saw as far as the beam widths you can see, but more importantly, if you look at the size that we came up with, this was by doing the interleave, and we were able to decrease the size to 8 by 8. So another thing we wanted to do was we looked at did a heat map comparison of both of the antennas in Ekahau. And this is at 2.4 with the Ventive antenna on the left and the Cisco antenna on the right. And as you can see, there's a little bit of a back lobe radiation on the Cisco antenna, but we wanted to change the scale so that you could actually see the heat map for both individual antennas. And then at 5 gig, I mentioned earlier when I showed you the patterns, there was a slight ripple in the Cisco's pattern, and we see it here as well on 5 gig when we look at the heat map comparison as well. So if I was to take this design that we had, I could take this and replicate it to do a 8-lead design for AX. And what I would basically do is I could replicate that 4-port design and make It's actually a non-port design because we've made everything symmetric with the antennas. But if you look at what we estimate the design to be is that with just the PCB, we're at 10 by 10. So we could almost get this design into the Cisco's packaging for their 4-port design for the D4M. That's it.